Hi everyone. This is a problem solution for chapter 10. So here we are going to look at various types of circuit. Once again, I'd like to emphasize that this is for the direct current, DC current. That means there is no time variation in the current. And also, in contrast to the DC, we will consider AC, alternating current, in the other chapters, but we are going to assume that there is a DC current circuit. So now look at the problem 27, a single loop. So start from the easy one. Single loop contains two resistors, R1 and R2, and two batteries, epsilon1 and epsilon2, okay, EMF1 and EMF2. And we are going to neglect the internal resistance of the batteries. So all the resistance are just simply R1 and R2. I find the current in the circuit. And we are going to take the clockwise direction as positive. This is clockwise is a positive. This is the I directions. Okay, so, and we need to find out I. Okay, let's see. So electromotive force, 1 is given, 2 is given, R1 is given, R2 is given, and the assumed direction is clockwise, okay, of the current. And then what we are going to do is that we are going to apply the Kirchhoff's loop rule. So we are going to start point A and travel clockwise around the loop until we return to the point A. Okay, that's the thing. That's the loop. So what we have now here is that batteries. Oh, I think that something is wrong. I think this is not right. Okay. So let's go back. Sorry about the mistakes. And when we apply the Kirchhoff's rule, whether it is a junction rule, where the currents are our main concern, and or the loop rule, where the voltages are main concern, the sign is very important. Sign is very important. So in this case, the sign conventions is given, clearly given. If you move from the negative terminal to the positive terminal, so negative to the positive terminals, like this, the potential change is positive. So from negative to positive, it is always positive. And if you move from positive to negative, just like this, if you look, yes, it is positive to negative, then you get the negative batteries. And for the resistor, if you move in the direction of the assumed current, in the direction of the assumed current, the potential change is always negative. That's the thing we need to figure out. And let's start from the A to B and C and D, then back to A. So from A to B, we crossed epsilon1, EMF1 from the negative terminal to the positive terminal. So here it is. And then it's minus negative to the positive terminal, so that it is plus. Okay. From B to C, so we have a current. And we note that it is our loop direction is same as the current loop direction and the current directions. And then is the same, so that as we state here, from here to here, we get the negative voltage difference. And then from C to D, there is another electromotive force. So we are looking at these directions from C to D, I'm sorry. And then we find out that is plus to negative. That means change is negative. So in other words, this part is a higher potential than this part. It is obvious. It is positive and negative. Okay. From D to A, we have a resistance. And then we see that this direction, so that it should be minus IL. And then summing up all these potentials, summation V is going to 0, so that this all together, we end up with this one. Okay. And then we can find out from this, we can find out I. I is given by this one. Okay. So important part here is the sign convention. Sign convention, I just want you to go back this part. This part is very important for the practical solution. And then consider circuit shown below. So I 1, 2, 3, 4, 5, 6 are given, and then R1 is given. Here's R1, yeah. 4 ohm is given, R2 is given, R3 is given, R5 is given, but the R4 is not unknown. But anyhow, we need to figure out 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All the currents are given, but the alpha is not given. And we need to find out V2. So in fact, V1 is not given. Okay. To evaluate the voltage source V2, we applied Kirchhoff's current law or joint law, and the Kirchhoff's voltage law, KVL, along with the Ohm's law, to determine the potentials at the specific node. So we have all the currents, resistance are given, and find the EMF for the battery V2. Okay, that's the goal. So what we are going to do here is that it's a kind of a routine. So I just want you to look at what is being done. Before calculating the voltage, the routine one is that let's ensure the current values are consistent at the junction of V2. So we call it A. So let's assume this junction. In this junction, we have I3, I4, and I2. So that coming in is going to be coming out. So that at node A, we have I3 and I4 is coming in, and I2 is coming out. So that it is I3 plus I4 should be same as I2. So if you look at it, so 1 ampere plus 2 ampere is 3 ampere. So that is consistent. Okay, so this current is consistent, satisfying Kirchhoff's current law. And then what we are going to do is that if you look at it, so this is what we want to find out, V2. So we can set arbitrary value here and then try to find out V2. But the important thing is that V2 is actually potential difference from here to there. Okay, so we can set arbitrarily, for easy calculation, we set that this position is going to be potential 0. Okay, so that's the thing we need to find out. So directly below the B2, as our reference point is 0 volt. And they calculate the potential at the bottom right corner. Here, you want to find out the current I5 flows through the resistance 5. So I5. And then we note that the potential drop across R5 is given by I5 times R5 and the 20 volt. Okay. So 20 volt is dropped as the current flows here. So that means position here and here, we have a 20 volt difference. And you can see that this is a higher position, and this is low position. Okay. So that this position is in fact 20 volt. Okay. So this position is 20 volt. We find out. Okay. And determine the potential on the right side of a vertical wire. So since there are no component between the bottom right corner, the potential at the right side of R3 is also 20 volt. Okay, that's what we said. Okay, this is the position. And then we are going to calculate the potential drop across R3. So we just did it for R5, and then it's time to think about V3. And then what we are doing is that we are looking at this loop, and then we note that the current I3 flows through the R3 and from the right junction toward the node A. So okay, it's going to these directions. So that this part is higher than this part. Okay, this part is higher voltage than this part. Minus plus. Okay, and then at the R3, VR3 is given by I3 times R3 by Ohm's law is 4 volt. Okay, that means since the current I3 flows from the right toward the left node, from here to here, the potential at node A is the starting potential minus the drop. Okay, so that's the thing. So let's try to find out what we have done. So note that we come up with a VL5, and we say that this is the B equal to 0, so this is the B equal to 0, and then means this position is 20 volt. And then if you look at it, it is same voltage as this one. Okay, there's no resistor or no battery, so that at this point and this point is same volt. So it is a 20 volt. And then it is reduced by this resistor by 4 volt and is 16 volt. Okay. So we have a 16 volt here. So what we are doing here is that V2 is an unknown, and we are noting that V2 is related with the VA here and the V equal to 0. And in order to find out VA and the V0, we note at this loop. And then we first found out a voltage drop across this R5. And then we note that from this and this, we have same voltage so that it is the 20 volt. This is also 20 volt. And after this ohm resistance R3, the voltage drops to 16 volt. Okay. And then we are very close to the end. And the VT is nothing but voltage at A minus voltage at the bottom, and this is the 16 volt. So if you go back, we are looking at this segment. This segment of the loop. The reason why we have chosen is that we have this R5, R3, top and bottom, and then we have a voltage here. So that this is one thing. Of course, we can choose this one as well. But judging from the current flow, it's more intuitive, such that voltage drop is happening across this one. And then the way we did was to, so that here is the I5 this way, 5, R5. And then here comes S3. So what we have found is that set this position as a 0. This is negative. And then we try to find out what it is, the voltage. And then we note that here is the same. And then from this to A, we find out the voltage drop. And then we find out VA, voltage A, and then this one should be the same as the voltage 2. Okay. Now we have a very similar situation. In this case, we need to find out R4. In previous case, we were given a problem to find out what the V2 is, but now in this case is R4. Okay. So now let's try to find out how we can do. So what we are trying to do is that we will determine the potential at the junctions by analyzing the right side of a circuit first to find out the voltage of the source V2. Okay. And then we are going to find out R4 on the left-hand side. So that in this loop, we are going to find out V2. And then once V2 is found out, and then from this loop, we are going to find out what the alpha is, number 2. Okay, that's the strategy. So now we know the current, we know the resistance, and the goal is find out what is alpha. And then Kirchhoff's current law, at the junction, incoming current should be same as outgoing current. So that at the center node above B2, this is A. And we note that once again, I3 and I4 is incoming. I3 1 ampere, I4 2 ampere. And then I2 is 3 ampere. Okay, so it is consistent. Okay, so we check the current rule satisfies. And then what we try to do is that, as we had done before, we're going to set the bottom junction below V2 here, B. I5 enters, and I4 and I6 is leaving. Okay, so I5, I4, and I6. Okay, so it is also consistent. Okay. So what we are going to find out is the left junction, node L. L is here. I2 enters, and the I6 is also enters from this I2. And then if you look at it, I2 comes, I6 comes in, and then there is a I1 is actually leaving out. Okay? And then this is also consistent. At the three junctions, we found out that LAB, the Kirchhoff's junction rule or current rule is also, they are all satisfied. And it's time to think about how to determine the V2. This is a kind of a checking process, so we have to do it. Otherwise, we may get some mistakes, okay? So we find the bottom junction as our reference voltage point. Once again, similar to this is a minus, so that it is kind of a ground, so 0 volt. We will travel through the right loop, to find the potential at the center node here. We want to find out. So that we are going to potential at the bottom right corner here. So current I5 flows here, so that this part is a higher potential than this part, okay? And delta potential R5 is given by I5 times R5 is 15 volt. Since the current flows from the corner to the 0 volt point, bottom right corner is, here is the V bottom right is 15 volt. Okay, so this is the 15 volt. So 0 volt. And then we found out that this is 15 volt, and then this is also same 15 volt because there's no resistance. So that is the 15 volt. And then we need to find out what's the voltage here. And we note that voltage will drop by this resistor R3, and the voltage drop is given by this much. Okay, so at the VA is going to be 10 volt. And then what we know is the V2 is connected between the 0 volt and the 10 volt. We know that, okay, this is the 10 volt. So now it's time to find out what the alpha is, okay, for this loop. And the potential at the left junction, VL here. So this is the 10 volt, and then it is, so this is a higher potential, and this is low potential. And then we note that this is due to this resistor. So on the resistor, we have a voltage drop caused by resistor with the current. It's going to be 15 volt, okay? And then at this part, so it is dropped by this much, so that VL is VA minus 15 volt, is minus 5 volt. So at L, it is minus 5 volt, okay? So note that here, and calculate alpha, the current I6 is flows from the bottom wire through the alpha, like this, to the left junction, which is minus 5 volt, okay? So that here is the 0 volt, and then minus 5 volt. So it is higher, lower, it makes sense. And then I6 times alpha should be voltage drop. here, so that what we can get is that I6 times R4 is 5 volt. That is what we need to find out. And R4 is given by 5 volt time divided by the R4 in ohm. Okay, that's the way it is. Okay, here it is. Oh, this is I6. Sorry, 6. 5 volt. R4 is 5 volt divided by I6 ampere. Sorry about that. Okay, this is the same as this one. And another one, this is the same as before, but we have to find out V1. Okay. Thus far, we were dealing with a loop here, and then the loop there, something like this. And then we were dealing with the V2 and R4, etc. And then we are going to do the same thing, same logic, and then we will finally find out what the V1 is. Okay. So we know I1, I2, I3, I4, I5, I6. All the currents are given. And the R1, R2, R3, R5 is given. Okay. But the R4 is not given. And the V2, V1 is not given. Okay. And we need to find out V1. And if you look at this, so we are going to do several works to eventually get the V1. Okay, so now let's find out what we can do. Similar to what we have done before, we said this is the voltage 0 point. Okay, and we'll move through the circuit component to find the potential at this V1. Okay. And calculate the potential at the right node, here VR. The current I5 flows from the junction on the phi line I5, and then is flowing through the R5, okay, to reach the ground zero volt. And then, according to this, is given by simply current times resistance is 18 volt. So that means VR has 18 volt. Okay, this is voltage drop is 18 volt. That means this is higher. This point and this point is the same, so that the VR should be 18 volt. And then what we are going to do is that we need to find out potential at the top wire, V top. Okay, so we need to find out what it is. The current I1 flows from the top horizontal wire through the resistor R1 to the right node. So note that it is going through this one. Okay. So potential at the top wire is V top is VR plus delta VR1, which is I1 times R1. Okay. And then it is 38 volt. Okay. This is 38 volts. And then now what we are going to do is that we need to find out center here, and that can be easily found out by the ohmic resistance, voltage difference by the resistance, and then delta VR3 is given by 4 volt, so that center volt node is by this much it is lower. Okay, so that V center is 14 volt. And then calculate the potential at the left middle point, left middle node, VLM. Yeah. And we note that it is I2 and R2. So this will give us the voltage drop, this much, okay? Such that left middle node here is that lower by this much in comparison to the center. So 14 volt is at the center, and then voltage is dropped. And then by how much is 12 volt, so that VLM equals 2 volt, okay? And now the voltage source is connected between the top wire and VLM, such that V1 is V top minus VLM is 38 minus 2, 36 volt. Okay, that's the thing. Okay, next we are going to have a different set and consider circuit below. The voltage 1, 2, R1, R2, and R3 are given. And we are to find out what is the current I1, which is flowing through the resistor R1. So we have this given thing, and then apply Kirchhoff's junction rule. We look at the bottom center, which one? This one. And then note that it is incoming, and outgoing. So we have this relationship. You say this equation 1. I1 plus I3 is equal to I2. Okay, that's the first equation we have. And we are going to apply the Kirchhoff's loop rule. Left loop 1 is this loop. This one. And for the loop 1, we are starting from the bottom left corner and moving clockwise like this. So go up through the V1, okay, from here to here. The voltage is given is plus V1, okay, and go down through the R1. Okay, there should be voltage drop minus IR1, and then there's another voltage drop by I2 R2. Okay, and then we note that this sum of the voltage is going to be 0. That's our Kirchhoff's rule. So this is the equation 2. Okay. And then loop 2 is that starting at the bottom center here, and then moving counterclockwise. This is loop 2. Think about this. And then going right through the R3. Okay, so we are looking at this direction. So it is, now you have a voltage is, the direction is opposite to the current, so that it should be the positive, okay? I just want you to know in this case, our direction of the movement is same as the current, then the voltage drop across the resistor is always negative. But we take this loop, and then what is going to happen here is that our direction is opposite to the current, such that the voltage would be plus. And then we have a minus sign here, okay? Minus plus, so that we have a voltage 2. This plus, okay? And then it's going here, and then we have a same direction as I1, so that the voltage drop is minus. And this sign is absolutely important. And then we end up with equation 3, okay? So now we have a 3 equation with the 3 unknowns, I1, I2, I3, and then this is equation 1 to 3. And then we can plug in the equation 1 into 2, and then to get the more reduction. And then we get I3 is given by 13 times 7 I1, and then express in terms of I1 from the equation. And eventually, you will end up with the equation only for the I1, okay? And then you can find out I1. So basically, we have 3 equations, and then we have 3 unknowns. We can find out all of them. Okay, now we have a different situation. So V1 is 11 volt, V2 is given, so that given values are shown here. Yeah, and then we need to find out I2. Where is I2? Yeah, this is what we want. So establish node potentials, top horizontal wire as our reference. So in this case, we have a different load. Usually you can always have a different situation, but if you look at this, there is no element. So that means from here to here is the same potential. So that it would be better to set this is the V equal to 0 rather than this part, okay? So we are going to set this the 0 volt and the node B bottom left here. And then we need to find out this is the 11 volt, so that you should have minus 11 volt, okay? VB is minus 11 volt here. Node D here is also can be found out. Similar to the case of this case, if you look at it, this is the 0 volt. And then it is connected only by this battery. So that VD is actually minus 6 volt, okay? Same as the V2. If you look at the voltage 2, it is a lower, higher. And higher part is a 0 volt, then obviously VD should be minus 6 volt because V2 is 6 volt, okay? V1 is 11 volt. So now we know that VB is minus 11 volt, VD is minus 6 volt, okay? That's what we know. And then what about the node C? And we'll call it as a VC, okay? Using the current direction labeled here, and from the formula, I is given by this one. The current I1 is flowing this way, and that I3 and I2 is this way, okay? So that what is happening here is that here is the 0 volt, and that this is the VC. So for this element, voltage drop is 0 minus VC, and then R1 is 5 ohm. So that I1 is given by, so voltage minus VC divided by R1, okay, which is 5 ohm. So we know what the I1 is, okay, and then flow from the node D, here, node D, we note that is minus 6 volt. And then if you go back, this is minus 11 volt. And we found out I1, and then it's time to think about here and here. So voltage difference is VD minus VC, okay? And I3 is generated from voltage drop and this resistance. So that R3 is there. Okay, so we find out what is R3 is. Note that I1 and I3 are given in terms of a VC. And then now it's time to think about I2. I2 is given by from here to here. So VC, VB, VC minus VB over R2 here. And then what we want to make sure is that we are going to apply the Kirchhoff's current rule. So incoming is going to be outgoing. So that in this case, I1 and I3 is incoming. I2 is the outgoing. So that if you do the same thing here, then everything is changed into VC, okay? And then once we know the VC here, and then we note that I2 is actually here. I2 is here. VC plus this one. Okay. And then eventually we can get what we want. Find out I2. Note that this will give us VC and this will give us I2. This is our final result. And now a hot pacemaker fires 70 times a minute. Each time a 25 nanofarad capacitor is charged to its full voltage of 0.5 volt. What is the value of a resistance, assuming that battery is in series with a resistor? So it's time to think about what is happening here. So once again, the capacitor is charged and then discharged. Okay, that's the thing we need to find out. To find the resistance in the pacemaker circuit, we model the timing mechanism as an RC circuit, as it is. And the firing interval is determined by the time constant of a capacitor charging through the resistor. Okay, so it takes certain time to charge and then fire, and then is discharged. Then it takes certain time to accumulate charge on the capacitor and the fire, and that's the way it is. So firing rate is 72 times per minute, and capacitance is given. Voltage is given. Okay. Here, the calculate the firing period is that Since there are 60 seconds in a minute, so 60 seconds, number of bits per minute, so this 172, and is about this one. Okay, period P is this second, about 0.83 seconds. And then we are going to apply the tau is going to be, in the RC circuit, time constant is given by R times C, and then this equal to with us our period. And then we can find out R is given by this T divided by the C. So this problem is not exactly solved, but what we can do is that as a ballpark, we assume that it takes time, RC, to charge. Remember that in the charging cases, the RC is the time constant to fill the capacitor into maximum charge. Okay, and then if you discharge, once again, RC comes in as a time constant, so that it is absolutely important to know that the time constant in this RC circuit is determined by R times C. How is RC? Charging or discharging. So what we have found is that the time interval, and then we set it as a time interval is same as the R times C, okay? And then R is given by T over C, okay? Now let's look at another interesting one. So this is very important. I think this is interesting. So here the assumption is this capacitor has been connected for a long time. This is the important clue. What is the absolute value of the voltage across the capacitor? The voltage across, let's say, from here to here, okay? And then it is absolutely important to know what does it mean by a capacitor has been connected for a long time. That means it took the RC curve and then it reached the maximum charge, okay? And then when a circuit or container capacitor has been connected for a long time, that means capacitor reaches the steady state. And then in a DC circuit, and the steady state, capacitor acts as an open circuit. As it looks like it is open circuit, it's not connected, okay? So no current flows through the branch containing a capacitor. That means from here to here, there is no current, okay? Okay. Since no current flows through the center branch, the circuit effectively becomes two parallel branches connected to a 10-volt source. So it's kind of looking like this. This is not connected, so that it looks like one is one branch. Okay, I should write in this way. It's not, let's just forget about the drawing. So R1, R3 is in the series, so that you have R1 and R3 in series. And then there is a R2 and R4. Then it is connected by V. And this is same as this one, okay? The reason why is that C capacitor acts as a kind of a open circuit in this case. So it is there is no current and whatsoever, so that it is separated in these two parallel. So note that it is parallel. So it's a parallel. Okay. So the left branch is series in the R1, R3. Right branch has a series in the R2 and R4. And then what we are going to do is that voltage divide rule. So series combination of two resistors, RA and IB, then we get this relationship. And then uh, I wonder whether we have to think about it. There is a series combination of a two resistor, A, B, and then we have a voltage here. And if we want to find out so in this case, we find out voltage is, note that I is given by uh, I times RA plus RB becomes B by Ohm's law, okay? And then we find out I is given by I is RA plus RB. And then in this specific voltage difference is given by I times R, I'm sorry, this is RB. At the RB, this is the output. And then V out, let's say this is VB, is I times RB. Then it is RB, RA plus RB times V. Okay, just plug in I. Okay, let's assume that bottom Y of the circuit is our reference groove, reference volt ground. Okay, bottom is 0 volt. And at the left node is junction between the R1 and R5, and then this is given by this formula. And right node is given by this formula, okay? And then voltage across the capacitor is given by, which is this one, okay? So let's try to find out what is happening. So we find out voltage. Let's say this is the common ground. So we found out here voltage, and we found out the voltage here. And then the voltage difference is from to here to there, okay? So that's the final answer. And it is similar, but the condition is different. capacitor has been connected for a long time as before, but if the battery is now disconnected, so that means the charge accumulated in this capacitor is now discharged, so that there should be the current flowing. And how long does it take the capacitor to discharge? 1/7 in its initial voltage. Okay, that's the things. So it charged with a certain voltage, maximum voltage, and then it is discharged. So initial state, as before, it acts as an open circuit. Okay, and then is fully discharged to an initial voltage of a V0. And discharge state, and the battery is disconnected. And in this specific configuration, disconnecting the battery leaves the top and bottom wires common node for the resistance. Okay, resistors, top and bottom is now common. So it is gone. Okay. And then in this case, what is going to happen is that as soon as the voltage is cut off, then now you have a certain current flowing from the capacitor. Remember that at the full stage, there is no current at all for the DC current. But in this case, you will flow positive charge or negative charge will go a certain direction so that it will lead us a certain current. Okay. So in this case, if you look at it, then what's going to happen here is that flow is and this is disconnected. That means this part and this part is same, grounded. Okay. And when the battery is removed, the capacitor will discharge through the surrounding resistors. There are two parallel paths for the current to flow from left terminal of this capacitor to the right terminal, from here to here. Path A is through the R1 and R2 here. And the other one is from R3 and R4. Okay. And then we need to calculate each path. Okay, so let's say this is the RA, R1 plus R2 is a 7 ohm. This RA, RB is given by this one. These two passes, RA and IB, are as a parallel relative to the capacitor, such that equivalent resistance is going to be like this. Okay. And then what is going to happen here is that it's an RC circuit. Eventually, what is going to happen here is that this is the R equivalent and the C. Okay. And then in this case, our time constant is given by RC. Okay. And then we get this R equivalent. And then we get this one. And then we note that in the discharging cases, voltage is going to be like this, where the tau is RC. And then we set this VT as 1/7 of the original voltage, V0, V0. And then we get this one, and then we can find out T. Okay. Here. Okay. A capacitor with a capacitance of this microfarad. is charged to the full potential of 8.6 volt and then discharged through the resistor. Okay. And what is the when it is discharged by half of its initial charge, how much energy is delivered to the resistor? Okay, that's the thing. So we identify the capacitance and the potentials, and the final state is that the Q final is going to be half over Q0. Okay. And then relevant formula related to energy, and we get the capacitance and the voltage, and using charge we have a same law, same expression. Here, note that Q is CB. Okay. And according to law of conservation of energy, the energy delivered to the resistor is equal to the change in the capacitor's stored energy. So that delivered is the initial energy minus final energy. And note that we are going to use the Q. So initially, we start with we are given the capacitance and the V0. So that we have this one. And the final state, in contrast, we are given capacitor and charge. Okay, so we have this one. So that we have E delivered is given by, this is the U initial. So U initial minus one fourth of the initial, so that it is this one, and then initial is given. Then you can find out energy dissipated by the resistor. Okay, now let's look at the other problem. What is the current in the R2 resistor? Okay. So here in this case, we have an internal resistance as well, small r, and then we have to consider all of them together. And we simplify the circuit starting from the most nested part, parallel combination of R3 and R4. So this one is going to be change it to R34. And R34 is, if you look at it, this is the parallel, so that we get R34. So now we have R1, R2, and R34. Okay. And combining R2 and R34, so that the reason why is that this one will give you R234. So we have this one. And then combining R1 and R234, R1 and R234, we get R1, R234, okay. And then we get it's parallel, so that the top is given like this. And then we have eventually we have sorry, so top R5, So, R voltage. Then that they are all serial. So that R equivalent is going to be okay. Eventually, we get this one, and then utilizing the total current is given by this one, and we get this one. And to find the voltage across the parallel capacitor, V top. V top is given by I total times R top. Okay. And then solve for the current in R2. Since R2 is the branch that has the equivalent resistance of R234, the current flowing through R2 is the total current for that specific branch. So R2 is given by this one, and then eventually we get this two. Okay. So it's a kind of step by step. It's nothing complicated, but I just want you to follow each step one by one. And what is the equivalent resistance of circuit connected to the battery in figure below? So it looks a little bit messy. Okay, but what I'm going to do is that uh, identify the part that is clearly in series with the battery. So yeah, and then here. So this is the resistor, and then everything here is, we call it RCA. Okay. And then we need to do the analyzing circuitry, this part. So if you look at it, these two resistors on the bottom left pass here. Resistor, resistor part. Okay. So know that the bottom left corner, this part, connected only, they are in series. So BA is given as a 2R. This 2R connects node B to node A. This node A, node B is connected by the 2R. And then step B, now between the B and A, you have a two parallel paths. So one diagonal resistor, BA here. And then there's this part, 2R, okay, right, between the B and A. So that RBA is kind of a parallel parallel resistor with the R here and the 2R. So that RBA is going to be parallel with RBA. Okay, so that we get this value. And step C, the path to C to B, C to B, and then A. And C to B, there is the top resistor R here. And then B to A, we have found out this one. Okay, so that we get this value. And this path is in parallel with the direct C to A. Note that this branch out and this branch out. And these are all parallel. So RCA is nothing but here R, and this one. Okay, so that we end up with this value. And add a series resistor on the top right here. And then we have a equivalent is given by this one. And plug in the 7 ohm, then you get this one. So a little bit complicated, but once again, you have to do it with the patience and with the correct setting up. In the circuit below, suppose all the capacitor is the same. Determine the charge on C4 if the voltage V over 11 volt is applied between the points A and B. Okay, so this is 11 volt. So what we are going to do is that once again, we are going to reduce the parallel to the equivalent capacitor. And then if it is a serial, then we will do the same thing as well. So in the capacitor in series, we have this one. In parallel, we have this one. And capacitance definition is given by Q is C times V is this one. So now if you look at it, the first, these are in series, and this one and this one is in parallel, and all of this and this one is in fact in series. Okay, so you need to find out those things. So combining of a C1, C2 is in series, and the combination of a C12 and the C3 was parallel. This is a C12. So C12 and C3 is parallel. And then as a result, C123 and C4 is in this series. Okay, so we get the C123. And the total equivalent circuit is in series because this one, then we get the equivalent capacitance. And then calculate the charge on C4. Okay. We note that so total charge provided by the source is the same as the charge on each individual component in the series string. So therefore, the charge on C4 is equal to the total charge of the circuit. Yeah. I think that this is the important part. In a series circuit, total charge Q total provided the source is the same as the charges on each individual component. So in other words, if there is a voltage here, so C1, 2, 3, and C4 in series, then we have a same Q. So if you go back to capacitor, you will find it, okay? So Q4 is going to be Q total, and then it's going to be this one, C equivalent times voltage, then Q4 is this one. Okay, that's it. And I think that this chapter 10 is kind of a little bit tedious. But if you do not take care of each individual step, then I think that there might be some mistakes. So it has a very difficult part. Not it is a high level. You may end up with some mistakes. So in chapter 10, you had better reduce the mistake as much as possible. Okay, good luck with your exams for this chapter 10.